Ladies and gentlemen, boys and girls, people who clicked on this video accidentally, welcome to the very first annual line following Grand Prix hosted in the lovely, dusty Tommy B garage. I'm Tommy B, joined with my co-host Tommy B, and let's get into this race. That's right, Tommy B, we have 3 robots in this cutting-edge new racing circuit, all competing for the top spot. So without further ado, let's take a look at our contenders. Just looking at these robots, I can tell this is gonna be an interesting race, right, Tommy B? That's right, Tommy B. And just like your mom, none of these robots are winning any beauty pageants. Dude, that's your mom too. We're like the Let's go down to Tommy B on the field to get some on-site reporting. Hello, Tommy B? Yeah, so obviously the only explanation is someone must have taken my pants off while I was sleeping and pooped in them to put them back on me, you know? Like obviously. Hey, hello, Tommy B. Oh, you're on the air. Hey, how's it going? You're live on air, Tommy B. Sorry about that. Let me go ahead and introduce you to the 3 contenders. First here, we have the Crowbot. This robot was sent over by Elecrow to test out. It was a kit made for children. Let's see how it stacks up against the competition. Our second robot is what I like to call the Woulda, Coulda, Shoulda robot. This robot is the robot we should have made when we participated in that hackathon. But you know what? Hindsight's 2020, right? And now, our very last robot, one of my favorites. It's certainly no looker, but this is supposed to be the fastest robot on the track. And even though it is so ugly, I still saw it parked outside your mom's house last night. Don't you mean like your mom too? Yeah, sure, whatever, dude. Anyway, it's time to get into the time trials, which coincidentally is also what your mom calls. Okay, dude, that one doesn't even make any sense. Like, oh, looks like the race is starting. I just feel like you've been really trying hard to like force this journey.
5, 4, 3, 2, 1.
Wait. Before we go through the results, why don't we go through the whole project from the beginning?
Hey, I'm Tommy B, and I was in a William Osman video.
Oh, yeah. I guess we are.
Well, kind of. I mean, I was in it, I guess you could say. So a few months ago, William Osman and Opensauce hosted a hackathon, which they called Sauceathon. The goal? To create a line-following robot that completes a chaotic and challenging course. I got to attend, which was awesome, so huge shout out to them and thank you for the invite. I had a great time. Now, despite having some very, very smart people on my team, I am sorry to say we got dead last. Also, for some reason, our prize for last place was an 8-inch knife. I'm not really sure what that's supposed to mean. Here's the thing though, while our robot did get last place, I am happy to say that our robot was one of the only ones that actually could solve a specific part of the course, and that was this red line section. See, the red line section was created to throw off robots using infrared sensors, which is typical on a standard line following robot. But we noticed that immediately, rejected IR, and did something completely different. And because of that, we were able to go through the red line section with ease. However, to get points for the red line section, you actually needed to get to the red line section, and that's where we fell short. For whatever reason, during the final runs, we kept getting stuck on one of the corners in the beginning of the course, and we couldn't make it to the red line section. I have no idea why this happened. Our robot was fine before, but for some reason, we couldn't get there, and so we weren't able to complete that section, which probably would have had us win. So, like any totally normal and well-adjusted human that I am, totally normal, I completely spiraled, rebuilt the course in my garage, and spent the last 2 months building robots in the dark listening to dramatic anime music. Lights went out. Maybe it's time to call it a day. Why? Redemption arc or something, but also this is a really cool project and now you can watch me do it better than I did in the Sauceathon. Also, I'd love to maybe inspire anybody to build line following robots. I think it's an excellent engineering project, especially if you're just getting into engineering or if you already are an experienced engineer. I'd love to see more line following robots pop up on YouTube and shared with me. That would be awesome. So in this video, I'm gonna cover 3 different line following robots, how they are built, how they are programmed, how they work, as well as how we solve the red line section, and what other challenges popped up along the way and how I fixed those too. So while you're here, hit that subscribe button, leave a comment below telling me how totally normal and well-adjusted and normal I am, because that's what normal comments say normally. And let's get into it. So to start this project, we're gonna start with something simple and a very basic line following robot. I got my table here, which I made. I'm gonna set up a quick course using some black masking tape. All right, and to demonstrate a simple line following robot, Elecrow actually sent me over something that they call their Crowbot. So we're gonna build this and set it up to do line following, and then we're gonna switch to some other colors of tape and explore what happens. So Elecrow sent me this robot kit for free, but this is not a sponsored video, so I'll let you know my actual thoughts on it, but I believe it's designed for children. This looks like scratch right here. All right, this might be my toughest test yet. Can I assemble a robot that was designed for children? Goes into the header. That's it, I'm done. Okay, perfect. Let's clean this up a little bit and let's give it a test. I put it on the course and I press 2. I did something wrong. Okay, so that was a bit of work. I modified the code to basically make the light sensors a little more sensitive. I think it's dark in here, and I also think the masking tape reflects the infrared light a little different than it does on the little thing that comes in here. I do have it working, so now we can do a quick demo of what a line follower robot will do.
Okay, just interrupting myself real fast to talk about the programming of the Crowbot. They have a wiki page set up where you can read about it, but they basically offer lessons in 3 different languages. That's Let's Code, Arduino, and MicroPython. Let's Code is that visual editor that kind of looks like Scratch. Arduino is what I'm going to be using a lot in this video, and then MicroPython is Python but made for MCUs. To edit it, I opened up the tracking project and looked at the code here, so I'm going to open it up real fast here just to show you guys what I did. But basically what they do to sense lines are these digital reads. I had to change these to analog reads and then do a little bit of tuning to figure out those analog values to then make it decide if it is or isn't on the line. One thing I also adjusted, which I did re-enable, but you'll notice, is that I got rid of this backwards feature and made it always go forward. Turns out backwards was good for this robot because it keeps it from driving off the track too far and then not losing completely where it is. So I do disable it here for a second, but I'll turn it back on later. But that's not super important. But what is important is that this robot's easy to use. It's set up for beginners. So if it's something that anyone is interested in, feel free to look at it. I would say it's a good place to start with this sort of thing. But now back to line following robots.
It's certainly not the fastest robot around, but it does a pretty decent job of scanning what's in front of it to stay between the lines. So if we leave it, it's just gonna keep doing this forever. But there is something I do wanna try and see what happens. So just like in William Osman's challenge, he replaced part of the line with red. As you can see, the robot can't seem, it tries sometimes, but it can't seem to actually detect the red line very well. To demonstrate it again, I replaced the corner with blue tape this time, which you can see it's struggling with, but at least it can actually see the blue tape. But the whole point of this, what I'm experiencing with right now, is that I don't think this is the right sensor to use, especially for the challenge that William had at his hackathon. And that is why we're gonna do something else completely. So to quickly explain why the infrared sensors aren't a great choice for going over red, is that it's having trouble differentiating between a surface that's reflecting all of the colors back at it, which is white, or a surface that's reflecting just red back at it, which is red. The infrared sensor can only see colors in infrared, so if something is reflecting infrared back the same way as the table surface is, it can't see it at all. Even though with our eyes we can very much see it, which is what leads me into the sensor we're going to use, or at least the sensor we're going to create for our line following robot. Nevertheless though, this is a very cool robot kit, very easy to put together. If you have any kids in your life that are interested in STEM, I think this is a cool platform to start on. It's pretty cheap. I'll link it in the description. Again, not sponsored, but pretty simple little robot, and it's a lot of fun. All right, so now it's time to go into my first robot that I am building. This is what I quickly made. All it is holds 2 motors and then has a spot for a breadboard, and then there's a caster wheel on the bottom. I just bought one of these from Amazon. If you actually compare, the design's really similar to the Crowbot, but it's kind of the opposite direction. Caster wheel's in the back on the Crowbot, my caster wheel's in the front. I did this because from videos I found on the internet, it looked like people who do a lot of line following robots do the motors in the back, sensor in the front, caster in the front. So that's what I did. But okay, this is not very interesting. Let's talk about the sensor situation. So for this line following robot that I'm making, I'm actually gonna use a color sensor, but not like a typical off-the-shelf color sensor. We're gonna make our own color sensor. And the way that's gonna work is with this. So this here, if you look, are RGB LEDs in the top and then something called a photoresistor in the bottom.
But Tommy B, what is a photoresistor? Well, I'm glad you asked, Tommy B, because
Nobody's allowed to watch my video without learning something. So let's talk about what a photoresistor is. This is a photoresistor, and what it is a resistor that changes value based on how much light it gets. With a lot of light, you have a low value. With no light, you have a high value. But how do I turn this into an analog light sensor? So here's some nerdy stuff. This is a resistor, this is a photoresistor. These are the symbols for them, and this is what we're gonna use. This is a voltage divider, which is two resistors in series. If you look at this, here's the equation for nerds, but the voltage here in the middle changes based on what the resistor values are. But since my photoresistor changes value, in the circuit I'm using is I put a photoresistor on the top and a regular resistor on the bottom, which is actually 10k ohms for my circuit, 5 volts. That voltage will change with how much light it is, and then you put it to the analog pin, and then you have different numbers based on how much light there is. That's the whole circuit. Cool. So if I quickly open it up, you will actually see this here is just one of those RGB strips you can buy off the internet. It's addressable. For William Osman's hackathon, we didn't get these. We got like actual RGB LEDs. We had a hand wire. But for the sake of this project, this is a little simpler and it's virtually the same thing. You can see this is where it all fits into place, shines through, and ideally each RGB LED will only shine light for the one photoresistor. They're kind of like separated. So like the thing will just mount on the front and it holds it just barely off the surface so we can get really close to scan the surface. So to test the robot, I actually hooked it up with an ESP32. If you've seen the very first videos on my channel, you'll know where this is from, but it's an ESP32 remote control. It's not set up to be a line following robot yet, but you can see here, if I press forward, it's pretty fast. It's pretty loud, but it's very fast. And ideally, that's what we want. I want to solve this line following thing as fast as possible. Unfortunately, I'm actually gonna have to rip out this MCU and use an Adreno Nano for two reasons. One is that for the actual hackathon for William Osman's event, he gave everyone Adreno Nanos to use. They're simpler processors, they're 8-bit, but he said this was plenty enough for the line following robot. So I'm gonna stick with that mentality for this project, as well as I need 5 analog inputs for this, sensor array I built. But the ESP32C3 that I'm using only has 3 usable, 4 technically if I turn off Wi-Fi, and that still isn't enough. They're also less accurate. The Adreno Nano surprisingly has a very good analog to digital converter, so Adreno Nano is the answer here. So unfortunately, I'm gonna have to lose my radio controlled ability, but that's okay. So first things first, I'm gonna get the Adreno Nano installed in here. We're not actually gonna get the motor going. We're first gonna start trying to set up the sensor and getting that working, but I'm gonna attach everything, build it physically before we start doing that. And I'll show you guys how I'm gonna read the data and how I'm gonna program it accordingly. For the actual RGB sensor, I do have to solder 3 wires to it: power, ground, and data. So I put a little hole in here for wires to come through, and that'll come into the bottom. I'm gonna have to try to keep it really neat. There's not a lot of room to work with. I don't know why I didn't make it bigger. My own fault. All right, made a bit of a mess, but I got it attached to the car. When I put it on the surface, it's just about 1.5 millimeters off the surface, which is perfect. I want to be as close as possible because I only wanted the photoresistor to read the light coming from the RGB LED. All right, cool. Luckily, I didn't break anything. I uploaded just the demo reel for the RGB LEDs. See, they're glowing. Next step, I'm going to wire the photoresistors into the analog inputs. All right, and there it is wired up. The only thing I need to do is add some resistors on the other side of this to create that voltage divider, and then we can start reading values after I write some firmware, which I'll show you. So to go through the code I wrote here in Adreno, it's pretty straightforward, but I set up fast LED to use the LED strip. I made a array of the analog pins. I put them in order just to make my life easier. I'm just setting it to white for now. We're gonna change that later. See, there's the analog values it is currently reading. So if I pick it up, you should see them all change. So then I'm gonna put this on the line, maybe like kind of dead center, and we'll see how some of the values are lower than others if I move it around. So if I just have the rightmost RGB, you can see it's at 600, everything else is around 200, 300. Slide it over, same thing, that one's higher, and the other ones are lower. How exciting. Cool, so now I'm gonna edit the code to actually go through the colors and then read as it goes. So I'm gonna have to expand my analog value array to have multiple colors per thingy. be interesting. So you see now I have 3 numbers for each LED. That is because it is flashing red, measuring, flashing green, measuring, then flashing blue, measuring. But if you were to look at it, it just kind of looked purple. Actually, it looks rainbow on the camera, which is interesting. But it's basically flashing through the colors so fast you cannot see them. And you'll see there's a pretty stark difference between this is white, I put it over the black, goes up. Okay, so here's the logic. It's really straightforward. I just made this is over line bool variable. It's true or false. And I'm saying for the red channel, when it's flashing red, if it's greater than or equal to that, or on the blue channel, if it's greater than or equal to that. This is like, I just took the minimum value from when it's over white, because it's always bigger, and I added 50 on each one, just to keep it simple. So now it's just displaying this thing here. You'll see it's over nothing, but if I move it to be partially over the red, a couple of them. And if I move it around, you'll see it's just telling me which one is true. And that's all the logic I need, really. Time to wire up the motors, and we're gonna take this data to tell them the robot how to move. Awesome, this is going pretty smoothly so far. All right, so I wrote some simple logic, maybe not so simple logic, that basically is just gonna tell it to turn based on how far off the line it is. It's pretty straightforward and there isn't really much control to it, but I mean, let's see what happens when I hook up the battery. I will say I'm not telling it to go all that fast just yet. I think that'll come later, okay? It's booted, it's running. So it's moving, but what's happening here is it's stopping sometimes, and that's because there's no conditions I wrote for when there's 3 of the LEDs over the line at the same time. But hey, I mean, it's going, and it's pretty quick. Yeah, so this is the condition where 3 of them are actually over the line at once. It has no idea what to do. All right, little bit of tweaking. Let's test it again and see how it goes. It's going way too fast. It's just sliding around. It's trying so hard, but it's got no grip. It's just sliding around. Okay, I think I need to slow it down a little bit. One second. Post-hackathon, I had a lot of ideas of how I would have done the robot differently, and now I'm finally able to implement them. Unfortunately, these ideas didn't come to me at the time, but this robot here probably would have made it very far through the course, just as is, and I've spent less than a day on this, which is the length of the hackathon. So, hindsight's 2020, I guess. But this robot does have a bit of an issue, and you'll see sometimes it oscillates back and forth on the line, and that is something that we're gonna try to deal with some fancier code. I'm gonna try to really clean up how I'm dealing with the logic of the motors. I kind of brute forced what to do, basically which LEDs over the line, tell it to turn by how much. But okay, I'm gonna go to my desk and work on the firmware again.
So here I am at my desk, and this is actually in the future. This is the final firmware I wrote for that line following robot. And as you can see, I implemented something called PID. This stands for proportional, integral, and derivative. And I know that sounds complex if you haven't heard of it before, but it's basically a sort of algorithm that will help you reach certain set points smoothly. So by doing so, I adjust a KP, a KI, and a KD value. You can think of KP as your gain, which is actually what they call it. And that's like how fast does it turn. KD is your like predictive value for a line following robot, like how much does it think it's going to happen on the turn. And KI is your long-term error, so it's trying to compensate for old error. This is trying to compensate for future error. This is trying to compensate for old error, and this is trying to compensate for current error, is one way to think of it when it comes to a line following robot. So the algorithm for it is actually pretty straightforward, but let's go into kind of how this works. So everything is very similar. I'm reading the analog data and I'm turning it into digital data by saying if it's greater than or equal to a value plus some offset that I added. And this goes for if it is flashing red or if it is flashing blue. That's what the double lines here mean. It means or. So this turns it into just a 1 or a 0, yes or a no. Is it over the line with that LED? And these LEDs correspond to them in a row. So then I call my PID controller function, and my PID controller function is all the way down here. And what it does first is read the position. And so position, what I did is I took all of those logics, the things that I wrote about all the different positions it could be in, and I translated them into just straight numbers. So my int position function here is taking all the different logic values of the is over line array and returning certain numbers based on its position. And it only goes up to 9. So when I do call it, I'll subtract 5 to make the 0 point in the middle. which is right here, with just this one over the line. There's also a couple extra positions I included. For example, there's this one where all of the LEDs are over a line. I'm returning -1 because I wanted to do something special when that happens, which we can look at here in a second. So yeah, I'm taking my position, I'm subtracting it by 5, which means that if error is 0, then my line following robot is in the middle, which is exactly what I want. So I'm saying if my error is 5, which is me returning 0 here, it says do the same thing. That's because it'll just remember the old whatever analog value I wrote to it before, and it won't change it, and then it'll continue on. Then 6, that's if I return -1 here. I am telling it just to speed up. I want it to go faster, and this will help me with a certain part of the course that you'll see in the end. And now here's where the PID bit works. So I have my P equals my error, I equals my I plus error, D equals error plus last error. So I'm keeping track of the error as I'm going through. So now my motor speed is taking now in account those KP, KI, and KD values, and I'm taking my base speed, which was a value way up there, and adding or subtracting my motor speed. And then depending on how big the value is, it can't be greater than 255 because that's how big of a number I can write to my motor driver. So I'm just basically clamping them with these if statements. And now I'm saying if it's greater than 0, that I want it to go this way. And if it's less than 0, I want it to go this way. This is a bit about how H bridges work, where you would write your speed on one of them and the other one you set to ground. Same thing for the right speed. And then that's basically it. It wasn't actually that all complex to add. I'm sorry if this does sound confusing, but I will link something in the description about a guy who made a PID line following robot. He does a very good job of explaining everything. And some of this code I actually kind of took from his thing. So that'll be in the description.
So I've implemented PID into the firmware as we just saw, but now comes a bit of a tedious part, and that is called tuning the PID. I basically need to like trial and error numbers just to see how it works. To tune the PID for the robot, I changed up the course here a bit. I want to see how it reacts on a straightaway to see if it's gonna oscillate too much, and I want to see if it can make this turn. It gets a bit tighter as it goes, but still like a turn we should expect on the course. If I plug it in now, I have a pretty high P value set, so we should see how it acts on the straightaway. That is the telltale sign of too high of a P value. As it was going on the straightaway, it was oscillating greater and greater, so I need to lower it. I'm also gonna try to bring up the speed a bit because I did slow it down a lot for this, and I want it to go fast. Test number 2. That was surprisingly pretty good. Let's look at it again. Alright, now I'm going to start to adjust the D value for PID. I wound up with a P value of 14, so I'm starting with a D value of 140, about 10 times more. Woo-hoo-hoo. That's pretty good. I'd say that's kind of good on its own. I'm gonna bring up the base speed and see what happens. The robot's slipping a lot. It doesn't have enough grip. It's trying, it's just not enough grip. I still think I can bring up the base speed, but that's too high. So I made a bigger course for the robot to go around, and one thing I found actually is that it slips a lot. So by moving the battery back towards the motors, I get a lot more grip, and so now the robot's like moving pretty quick. I think I can even get it going even faster. But first I'm gonna redesign the body to fit the battery on the back. That way the weight will be a little more distributed. All right, it's the next day. This is sleep deprived Thomas checking in. I did what I said. I rearranged the chassis so the battery is now on the back, hoping putting more of that weight on the back gives it more grip. I also redesigned the wheels here. These motors use something called a D shaft, which is like a flat side of the rounded shaft. And the wheels I was using before were just friction fit, they just fit on. So these wheels I designed actually have a D shaft in them, and I just stole the rubber from the previous wheels and put them on here. I also realized if you at home watching wanted to recreate my robot, these wheels that I have aren't really available anywhere. I bought them off AliExpress a long time ago. So I also designed up some wheels that use just rubber O-rings. So these are just really simple, 3D print them. They use the D shaft, can slide on the motor. So you'd be able to use these as well, and they have pretty pretty good grip on the table. I also added a button on the robot. It was getting really frustrating to have to unplug and replug the battery all the time to turn it on and off. So now I can just start and stop it with a button. Putting it back on the course, I've done no tuning. I've really just put it back together in its new form. And if we boot it, you'll see it actually has some oscillation problems. But what I am seeing is that it has a lot more grip. It is a lot more responsive. So I'm gonna go back and re-PID tune and see if I can get this thing to go faster. I wanna bring up that base speed as fast as possible, because that's really the goal here. I'm trying to just be overly fast. Yes. Oh. Lights went out. maybe it's time to call it a day. All right, so obviously I've been working on this for a really long time, but I think I've kind of come to a climax here. This robot, I'm sure I could squeeze out tiny little bits of performance, but I'm not really gaining much anymore. I think it's about as fast as this thing can go. However, I don't think this is good content. This is just a line following robot, and sure, it's fast and maybe it's a bit impressive compared to really basic ones. It's not enough for me. I want something dangerous and dangerously fast. So, in the name of good content, I went out and bought some stuff. Mainly, I brought brushless motors, the kind that go in those really fast RC cars you see in those YouTube channels, the things that can go 40, 50 miles an hour. I got 2 of them, one to power each wheel, and then I retrofitted it to fit inside of the original chassis here. You notice I had to give it a second level to really fit everything. It's a little ridiculous, but already I've found a problem with this platform, so let me show you. Okay, so here's the problem with this platform. These brushless motors are incredibly fast and incredibly strong. I hooked it up to the remote here to act a little bit like a RC car, but let me just barely press on the accelerator, just barely. But let me just press on the accelerator just a little bit, see what happens. It does wheelies. Look at this. Something that's also crazy here, the maximum amount of throttle I can get out of this that I put in the firmware is 15%. So this is 15% throttle. It's way too twitchy and just way too strong. So I need to redesign this whole platform, and let me show you what I've done. All right, so a few things have changed. I've redesigned the chassis of the brushless motor version, and we're gonna go ahead and assemble it. So it turns out that was all a lie. This car didn't work. So I redesigned everything. So if you watched the beginning of the video, you'd realize that this idiot right here has no idea what he's talking about, because that's not the final robot we wound up with. This is the final robot we wound up with. That's because I had to redesign this robot a total of 4 times for 5 different robots. That was because the first one I made was too fast. I didn't do the math for the gear ratio, and it turns out it'd be going like 37 miles an hour. Then that second one, which was really cool because I put this fan on the bottom. The idea was that like the fan would suction it down to the table and would give it more grip, which totally worked, but the robot itself was just too massive. It couldn't make the tight turns of the course. So I had to redo that. And then from there, it turned out it was still too fast. So I had to change the gearing one last time to wind up with the robot we have now. It wasn't the only thing I changed. I did find out with a robot going this fast that the photoresistors would actually take about 10 milliseconds to change. So I switched to something called photo transistors. Let me show you what that looks like. They look like little LEDs here, but these actually work just like photoresistors, and they'll change their value. I put pretty much, it's like a slot for slot replacement, but these can change value much faster in about less than a millisecond, which is perfect for what I'm doing. This robot is also running on an ESP32S3. I know the ESP32C3 I mentioned before didn't have enough analog inputs. This one actually does, the S3 version. And the reason we're going with ESP32 is because this robot is so big and heavy and moves so fast that stopping and starting it with my hand kind of scares me. So I stop and start it with the remote controller. On top of that, we get a much faster processor than that Nano, which will help for how much faster this one goes through the course. I actually also noticed in testing that these photo transistors don't really care if you're flashing through the colors or not. So one thing I did was just set the LEDs just to white and then read from the photo transistors. And that works really well and heavily improves my processing time.
And speaking of processing, here is the firmware for the final robot. You'll find that it's almost identical to the previous robot, except for my KP and KD values are different, of course. I've also included something called ESP Now, which lets me control it remotely. And one of the big changes too is that in my position function now includes 7 different LEDs rather than 5 on the previous robot. If I'm going to overcompensate, I really need to overcompensate fully. There's also a little bit of difference in how I write speed to the motor. This is using an ESC, which acts more like a servo, and so it's not an H bridge. So I have to like adjust my values based on that, and it's these like really long values. I'm using something called LEDC to write. That's like a proprietary function at ESP32. It's a little more complex in terms of how I'm making the ESC work, but I could use an ESC library theoretically and just go off that. But I just decided to go the manual way. But yeah. This is the firmware. It's not too much different, except for I'm not flashing red and blue like I said. I'm only setting it to white and reading the values from there. And I'm trying to run this as fast as possible. So I got rid of any delays. I got rid of any serial prints. And I just want it to just go as quick as it possibly can. And that carries over to the robots. So without further ado, let's take a look at these robots and how they perform.
So here is the final robot course I set up. Here is the start. It goes into some loopy turns. I did it in blue tape just for fun, but this is similar to Williams Osman's course. There were some turns up in the front, and then there's this here with these 45-degree turns. This was the part of the course that our robot could not get past for whatever reason. So I reenacted it here. This is the part I'm most interested in redeeming myself on. Then it goes from here into kind of like this horn-shaped thing they had on their course, which then you have to drive across the white paint without any line and then find yourself back on a line. And that's where I did the red tape. And then it actually comes back where it goes here, and then a similar thing, drive on the white, it'll get back on the course and run it all over again. Let's see how these robots fare. All right, I don't particularly have high hopes for the Crowbot, but let's see how it does. First turn done. This is where, oh God. You know, maybe we should check in on the other robots and see how they're doing. All right, it is armed and ready. Here comes the Woulda, Coulda, Shoulda robot. 3, 2, 1. All right, this one scares me because I'm scared it's gonna drive off the table because it just goes so fast. It'd be hard to react. I have to start and stop it with this remote, so I'm gonna pray for the best. Okay, ready, set, go. Sick. So there it is. 3 robots entered, 2 actually finished, and the brushless robot turned out to be the fastest. So I guess speed is everything when you completely overcompensate. But hey, this isn't the end. I'm actually thinking of redoing this project a bit. I know there's places I can improve, especially with the design of the brushless robot to make it as fast as possible. I'm actually thinking about applying to do an exhibit of Opensauce. So this is where maybe you guys can come in if you give me some feedback. I think it'd be cool to apply to exhibit at Opensauce and bring a line following setup. And I could do maybe like a mini hackathon where people could bring in their own if there's interest in this video. Or I could set up small robots that are pre-built that can be tuned with like a Bluetooth app, since I'll make them run on ESP32. I think that could be fun, so let me know what you think below. The deadline to sign up for an Opensauce exhibit isn't for another month, so I have some time to really sit on it and plan out what I'd want to do. So yeah, let me know if you're still this far in the video. Anyway, I got another DIY handheld in the works. I know most people who watch my channel are looking for that. That is coming up soon. Also, I'm at 9,900 and something subs. I said a while ago I was gonna do a stream at 10K, so if you want to sub and see that stream, definitely stick around. Oh, and if you think you can build a faster robot than this, I want to see it. Challenge me, post a video, tag me on Twitter, Blue Sky, whatever, post a YouTube video. I want to see a robot built at home that's faster than this one. Use masking tape as the lines, and let's see how fast you can make your robot. I challenge you. Anyway, if you made it this far through the video, please leave a comment below telling me how completely normal I am and how normal all this is. And thank you for watching. Overcompensating is a great idea, and everyone, I don't know what I'm saying.